Just before starting the talk, I was told that the group photograph, it might not take place if it's raining.
It will take place inside.
I don't know, but it's not sure. So now we have Mihai Ciucu talking about dimmer packings with gaps on electrostatics boundary interactions.
Okay, thank you very much to the organizers for giving me the chance to speak at this workshop. The outline of my talk is first I will give some background about dimer packings with gaps, and this will be basically the same outline as I did 2 weeks ago in the previous workshop, but it will be like 10 or 12 minutes or something. And then I will branch out in a different direction, in the direction of examining the interaction of gaps with boundaries. Okay, so boundaries came up in the previous talk, so hopefully there will be a connection. There's a relevant reference for this, a recent paper in PNAS, so it's available there. There are relevant references there. Okay, so we will talk about dimer coverings quite appropriately for today's topics, for the talks. So very brief, I mean, I don't have to define it. They were defined. The dimer covering, you know, you have sides on a lattice, and then a dimer covers 2 sides. And a dimer covering is a collection of edges which collectively contains precisely every vertex precisely once. Okay, and then even for this very simple case of the square grid, the question of finding the number of perfect matchings, it turned out to be a quite non-trivial one. So if you have the 2n by 2n grid graph, what's the number of perfect matchings? This was the dimer problem phrased in 1936 and solved 25 years later by 2 independent teams, Castelline on his own and Temple and Fisher. It used the Pfaffian method, which Professor Reshetigin talked about, and then it exploits the fact that you can use spectral theory and linear algebra to find the eigenvalues, and that's the determinant. That's just one example. Then you can look at the hexagonal lattice, and you can look at dimer coverings on the hexagonal lattice. This is such an example. For some reason, it's not very clear. So the black edges are not really there. So the background is the hexagonal lattice, and then the dimers are the colored ones, red, yellow, or blue. Just as in the square case, there's a dual picture. The dual of the square lattice is the square lattice itself. Dimers on the square lattice are the same as dominoes on the square lattice. Similarly, dimers on the hexagonal lattice are the same as lozenges or unit rhombi on the dual of the hexagonal lattice, which is the triangular lattice. So we get lozenge coverings, lozenge tilings of regions on the triangular lattice. So for instance, a classical example is this one considered by McMahon. If you take a hexagon on the triangular lattice with opposite sides of equal length, A, B, and C, respectively, then the number of lozenge tilings is a very beautiful number, a triple product of these simple fractions. Symmetry classes of these plane partitions were studied as well. So for instance, if the hexagon is regular, how many of these structures are symmetric with respect to one of the symmetries of the cube, right? So of course, this also pops up in 3 dimensions. This is a stack of unit cubes, and that's called a plane partition. And in fact, that's how McMahon thought about these structures. He didn't think in terms of lozenge tilings or dimer coverings, but they are quite equivalent. Okay, then another simple example. If you take the Aztec diamond, if you take this simple shape on the triangular, on the square lattice, this is called the Aztec diamond. This is the Aztec diamond of order 4 because you have 1, 2, 3, 4 things across. The number of perfect matchings, it's even much simpler than the previous 2 numbers. It's just the perfect power of 2. And this was found in the early 90s by Elkis, Cooper, Burr, Laxer, and Prof. And somehow this gave new impetus to the subject. Then you can look at finer things like how does a typical domino tiling look, and this is a tiling sample uniformly at random, and you get the Arctic Circle phenomenon, found by proved by Kohn, Elkias, and Prob in '96. These pictures are courtesy of David Wilson. This is a tiling sample uniformly at random from the set of all lozenge tilings of a large regular hexagon, and you get again this Arctic Circle phenomenon. So far we talked about the hexagonal lattice and the square lattice, dimers on the hexagonal and square. They are both bipartite lattices, and these were vastly generalized by Kenyon, Okunkov, and Sheffield in 2003 when they looked at general planar bipartite lattices with weights on them and classified the dimer models corresponding to them. For instance, Kenyon and Okunkov also explicitly calculated limit shapes which vastly generalize this particular example. And anyway, this is just a very brief outline of relevant work in the field. There's others as well, but the purpose of this outline is to highlight the fact that what I'm going to talk about goes in a different direction because it focuses on defects. So in all these results, you didn't have defects in the lattice. The boundary played a crucial role, and you got some, curves. The measures varied and things. But let's look at this very classical problem posed by Fisher and Stevenson in 1963. It's called the monomer-monomer correlation problem. So what is this? We go back to the square lattice, and we think of dominoes, not of dimers. And then a monomer is just a unit square. So we take a 2n by 2n square, and we remove two monomers. One is at the origin, let's say at 0, 0, and the other is at coordinates p and q. Now notice that one is white, one is black. Why is that? Well, we're thinking about the chessboard coloring of this board because clearly every domino will cover one black and one white unit square. So if you're creating defects and you hope to have dimer coverings of what's left over, you need to stay balanced. So you need to remove a white one and a black one, right? So what they propose is to do this, measure, so to speak, like in the previous talk, look at the number of domino tilings of what's left, and divide it by the number of domino tilings of the entire thing. You get a rational number. And they define the correlation function as follows in terms of these ratios. Keep this white monomer fixed at the origin, and keep this black monomer fixed wherever you see it. Maybe it's 5,4 or something, right? The coordinates have to add up to an odd number because it's the opposite color. And keeping this at 0, 0, and this at 5, 4, let n go to infinity. Okay, so this becomes larger and larger. You get ratios. I don't know what happened. Oops. So, well, I don't know. I guess it got unplugged or something.
No, I don't think so.
It didn't?
So something initialized and then disappeared.
I have my own laptop, so no.
He's coming, so he's coming.
He's coming. Well, but this is unplugged clearly, so
really?
maybe it just ran out of battery. Yeah. So sorry. Should I start my own laptop? Will it be faster?
It's okay.
Yeah. So anyway, this is a good time for questions.
Not for questions about the picture.
Yes, not for questions about the pictures. Okay. Right. So the idea is to study defects, right? Study defects, and just to anticipate the rest of the talk, we carefully send the boundary to infinity when I made this definition. So far there's no interaction with the boundary. That will come a bit later, like in 5 minutes, right? So, but nevertheless, this is it's a meaningful way to define this number as the limit of these ratios, and you get a positive real number, which they call the correlation function for the monomer-monomer, right? And what they did in their work is they conjectured the so-called rotational invariance of the monomer-monomer correlation. What that means is that if you keep the white one fixed at 0, at 0, 0, and you choose to send the black one away to infinity on the x-axis, then they noticed a decay as 1 over the square root of the Euclidean distance between the two monomers with a certain constant c, right? And then they said, well, let's do the same, but now let the black monomer recede away from the white one along the diagonal. Well, along a subdiagonal, because the diagonal is white, right? What do you get then? Well, they got numerical evidence which is quite convincing of the fact that you get decay as constant times 1 over the square root of the Euclidean distance with precisely the same constant, right? So then just based on these two cases, they conjecture that, well, it should be completely rotational invariant. And that's still widely open. And it's considered a very, very difficult problem. And for instance, I just want to mention that it seems to be in the same category, or just comparably difficult as the rotational invariance of the spin-spin correlation in the Ising model, because it's known that the spin-spin correlation in the Ising model on the hexagonal lattice can be mapped into the monomer-monomer correlation for the dimer model on the critical Fisher lattice, where the critical Fisher lattice is the following. It's obtained from the hexagonal lattice by inflating some air into each vertex and turning it into a triangle. Okay, and this becomes critical when the intertriangular edges have weight square root of 3, and the triangular edges have weight 1. So yes, it is true, but morally is the same, because then you average over the neighbors, and you're perfectly right. You're perfectly right, but then you get as this has the sum of 9 contributions, and if each is rotationally symmetric, then it will be rotationally symmetric, right? So
two dimer models are different.
Pardon me?
Two dimer models are different on this graph with additional vertex and without.
Well, yeah, but I mean, if you have the additional vertex, this has to be matched to something, right? So it's either this or this or this. So in some sense, it's a superposition of having 3 monomers where the monomer is undecided, in that sense, right? Okay. So anyway, Stanislav Smirnov, has this the wonderful proof of the conformal invariance of the Ising model, and those methods may well probably will lead to the proof of rotational invariance for a spin-spin correlation, but still it looks like a very difficult problem. And anyway, this is a counterpart of that in the bipartite world, because the interesting thing is that when you map an Ising model onto a dimer model, you get non-bipartite lattices. And the monomer-monomer correlation problem of Fisher and Stevenson is phrased on a bipartite lattice. So it's not clear to me how will this change things. Okay, so this, I guess my outline is becoming longer. Well, anyway, I have to struggle with the resolution, but these are just artifacts, right? So this is just a large rhombus on the triangular lattice, which I decided to turn into a torus for the following reason. I want to define, I want to explain which direction I'm going. The previous slide was the motivation, but now what do I do? What I do in most of this work is I phrase the analogous question on the triangular lattice, where the questions make perfect sense because monomers are just unit triangles, dimers are lozenges. It's still bipartite, right? You don't even have to color it because, I don't know, white points to the right and black points to the left. And suppose we have a more general class of defects, not just monomers. Suppose our defects, we enlarge our class of defects to triangular defects, triangular holes, of not necessarily unit size. So for instance, we have here 3 holes, and don't look just at two defects. Look at any finite number of defects. So here we have 3 defects, 2 triangular holes that point to the right, 1 that points to the left, of sizes 2, 2, and 4. How can I define a correlation function? Well, I can use the same philosophy. I can enclose them in a large rhombus on the triangular lattice, and I can try to take the number of tilings of the region with the holes and divide with the number of tilings of the region without the hole. But the fact is this boundary is so has such a strong forcing effect that the number on the bottom would be just 1 if you leave it as it is. So it's a much better idea to turn the thing into a torus, and then you have no boundary, right? You can then look at the number of lozenge tilings of the torus with the holes, divided with the number of tilings of the torus with no holes, take the ratio, and again pass to infinity for infinitely large tori, and that defines a number, right? So this is my number. This is the number I look at. And then what I managed to do is I managed to, in some sense, make progress on this conjecture of Fisher and Stevenson by proving what happens for a large family of holes, but the holes do not include the case of two monomers. So that's why the original conjecture remains open. But it does include the case of any finite number of triangular holes of any even sizes. That's one large class. And another class is you can have a single monomer. Everything else has to be of side 2, and the geometry has to be symmetric. These two separate cases I can prove. OK, so to phrase the result, I should tell you what you get. I need to introduce a system of coordinates. So let's put a black dot at the center of each vertical unit segment and declare one of them as the origin, to be the origin. Then take an oblique system of coordinates of a 60-degree angle, oblique system of coordinates with the x-axis going this direction and the y-axis going that direction. Then every black dot gets a pair of integers. It's coordinatized by a pair of integers. So I can give names to all these holes, right? I can say that the position of this hole is pinned down by the topmost black dot on its boundary. The topmost black dot here has coordinates 2 and 3. The position of this is pinned down by its topmost black dot, which has coordinates 3 and minus 2. And what are the indices here? Well, the index is positive 2 here. It means that positive means that it points to the right, and 2 means that it has side length 2. And the minus 4, the minus means that it points to the left, and the 4 means that it has side 4. Okay? So now we know what delta k of xy is, and delta minus k of xy is where k is any positive integer. Okay? So then my result is the following. I look at the following little movie, if you will. I have here the first frame of the movie is these 3 holes, much as they were before in the previous picture. But then what I do is I look at the topmost marked point in each of them, and I double its coordinates. Okay? And I keep the holes of the same size, but I shift them so that these base points, their coordinates are doubled. Okay? That gives me the second frame. Then I triple, it gives me the third frame, and you get this sequence of geometries, right? And for each of these, you look at the correlation function. So you get the sequence of real numbers. And this, if you think about it, is the natural analog of the question that Fisher and Stevenson looked at. In their case, it was just a monomer fixed at the origin, and the other went away, right? So this is the analogous question, which is, what is the asymptotics of this sequence of correlations? And this is the result that one gets. If the holes have arbitrary even sides, k1 through kn, remember k can be positive or negative. Positive means point to the right, negative means point to the left. Then you get this. So this long notation is just the correlation function, and r is the large parameter. R is time in this movie. So r is equal to 1 here, r is equal to 2, r is equal to 3. So as r goes to infinity, which is to say as this movie progresses along, the correlation function is given asymptotically by some constant times a Coulomb interaction. It's a Coulomb interaction. So it's a product of pairwise. It's a product over the pairs of the holes. And what you get is simply the Euclidean distance between the actual positions of the holes. So, as far away as the time r dictates. And then you raise to this exponent 1/2 ki times kj. So this is somehow, it governs this. So it's the distance to the 1/2 ki kj. Okay? So this is a Coulombic effect. And, if you go back to the Fisher-Stevenson question, what is, you'll get two monomers, right? So what are the Ks? Well, one will be +1 because it points to the right. One will be -1, it points to the left. So you get exactly 1 over the square root of the distance. So it's consistent with their conjecture. It's just that since it's more general, it unveils this electrostatic phenomenon. So it seems that this electrostatics governs this behavior. And it's two-dimensional electrostatics because if you take the log, this is a two-dimensional potential, and if you take the log of this expression, you get precisely, things that you have in Coulomb's law: constant times the product of the charges times the distance. And why are these the charges? Well, you could think that space is quantized and all the right-pointing unit triangles have charge 1, or the left-pointing unit triangles have charge -1. And then if you place a hole, it acquires charge just by displacing these quantas. So, pardon me?
These are the holes.
These are the holes. Yes, yes. So this is delta -4 of those coordinates. Yes. These are. I just wanted, to capture in mathematical notation the statement. I needed that notation. So, if a hole points to the right, sorry, it has, these 3 +1s and 1 -1. So the charge is 2 according to that, and 2 is just the side length. And similarly, if it points to the left, you get -2, so it's the signed side length. That's the charge. So anyway, all these considerations unveiled this phenomena for the case of no boundary, right? So the purpose of this talk is to say what happens if you do have some boundary. Okay. Yes.
Can you compute the constant C also?
Yes, I can. It's a very good question. In fact, this depends a bit on how exactly you define the correlation. I didn't give you one detail which you can realize. So, by seeming accident, the total charge of my holes is 0 here, right? So that's the simplest case when you can actually define the correlation function this way. If the total charge was not 0, you have to do something else, because then if you think about it, it's easy to see. If you take a torus and plug some holes with total charge non-zero, the leftover part has no Lozenge-Stylings, because the number of left-pointing unit triangles is no longer the same as the number of right-pointing unit triangles. So you need to bring in phantom charges and send them to infinity. And then if you normalize correctly, then the constant has a very simple expression. So let's call the normalized correlation by omega bar. Then the constant is simply the product of the correlations of the individual charges. So in some sense, it's quite satisfying that you can get this. And I conjecture that the same is true for any holes, not just for triangles like this, and in particular for monomers, and that gives conceptual meaning to the constant.
And you compute the corrections to the leading asymptotic behavior?
Pardon me?
You compute the corrections to the leading asymptotic behavior?
That's a very good question. I didn't look at it in this framework, but I have a second approach, which I will show in a minute. And with that one, it should be quite feasible to do it. I did not look at it yet. Yes. Yes?
Is it possible to explain what goes wrong for odd sides?
Yes. So I didn't tell you anything about how these things are proved. So I have two separate approaches. So the approach that proves this particular statement builds on work by Rick Kenyon, who found the coupling function for the hexagonal lattice, and he has this determinant formula originally for dimer-dimer correlations, but it turns out that it works also in the case when the holes are not dimers but triangles of even side. But you also need the total charge to be 0. So in that case, you can apply this formula, and then there's a pretty tedious task to actually work out the asymptotics using the formula, because the entries are these double integrals, these Fourier coefficients. But then I was able to generalize that formula for the case of non-zero charge and prove this. But what is the key fact for the existence of this determinant formula is the Pfaffian method. And there's this basic fact that for even holes, if you have a Pfaffian orientation of a graph and you make an even hole, then what's left is still a Pfaffian orientation. And that's not true for odd holes. And this somehow makes...
Find a new orientation.
Yes, exactly. You have to perturb the Pfaffian, like Fisher and Stevenson do in their paper. And it's interesting that the second approach I have is quite different. It's via exact enumeration. It uses the Gestel-Vienot method. And there also is bad to have odd holes. So for seemingly a different reason. But somehow I can handle exactly one odd hole I can handle because in the symmetric picture, because I have a way of cutting the regions in two using a factorization theorem I have, and then the monomer becomes on the boundary of the two halves, and so that's the reason. And perhaps I could handle two monomers along special directions, but not in general, because the symmetries are rigid, so there aren't too many symmetries. Yeah, but that's an important thing. Okay, so what can we say about the boundary? Okay, so here's another way to define gap correlation, and this will lead us into the second approach I have in proving such things. So suppose you have this symmetric distribution of holes, right? And you want to define, again, a correlation function. So previously, I would say, well, let's include them in this torus and do what we did. But you see, we have quite a bit of freedom in what regions we choose to include the holes in, right? Fisher chose the squares. Previously, we chose the tori because all these determinant formulae work for tori. But we could, for instance, choose this sequence of shapes. We could choose to include them in large hexagons, right? And then we could, the question is, how do we define the correlation now? There is a slight fine point, because you couldn't just say that, well, let's compute the number of lozenge tilings of this and divide by the number of lozenge tilings of the entire hexagon with no holes. Because, again, we run into the same phenomenon. When the total charge of the holes is non-zero, the complement of the holes has, so to speak, also non-zero charge, and it has no dimer coverings. So that definition doesn't work, but you could just shift the holes into a reference position. Because after all, what you divide by is just a normalizing factor. It's an overall normalizing factor. It doesn't matter. So you may shift them as close as possible to the monomer and use this geometry as the normalizing factor. So my assumptions here are that I need a symmetric distribution of holes. I need a monomer on the symmetry axis, and everything else has to be offside too. Okay, and then with this construction, I could certainly take the ratio of the number of tilings of the hexagon above with the holes and the number of tilings of the hexagon below with the holes, right? And I could again keep them fixed exactly where they are. Send the boundary of the hexagon to infinity, and I will get a number. So let's denote this number by omega. There's no head. Previously, I had a head because they were tori, but this more closely resembles Fisher's definition, so I didn't put a head. Okay. Of course, I didn't make this choice at random. I made this choice because I can express the number, these two numbers, in a meaningful way as multiple sums of round terms, a round term being a product of linear factors, manageable terms. Anyway, so if you define the correlation function as before, I was able to show, and in fact this was the first, I proved first this one, and then I proved the other one. I was able to show that the asymptotics is still given by the electrostatics picture. And it's interesting, the presence of the monomer is interesting because, it shows that there's nothing wrong with the odd holes. It's just that, it seems that for technical reasons, it's harder to get your hands onto the odd holes. But, the phenomenon still works. Okay, so an essential ingredient of the proof is the fact that if the holes are collinear, this number of tilings is a very, very nice number. It's as nice as McMahon's number. Remember, McMahon's number was this triple product of simple ratios. So here, the number of lozenge tilings of hexagons with holes like this, it's morally just as nice as that. If you want to write down the formula, it takes a full slide because there are many factors and many products, but every single factor is linear. So it's as good as you want, as you could hope for. And in particular, just using Stirling's formula, you can find any asymptotics you want. And you can find even boundary effects because these holes can be anywhere. So this is one advantage of this second approach, that even though it deals only with more restricted geometries, it gives you more powerful results, right? So as a very special case of this geometry would be the following. Suppose you have just a monomer, and I don't know, two triangles of side 2 touching one another, and then no hole below. And then notice that the yellow lozenges are forced, right? So if you want to cover this unit triangle by a lozenge, there's no choice but this lozenge. Similarly, here, there's no choice but this. This will force this one, and these two force this. So all these are forced. So these three holes are equivalent to a single hole of size 5, right? And for this situation, we have an explicit formula. So in particular, we can easily find the interaction of this hole with this boundary. So we call this a constrained lattice boundary. So it's constrained because lozenges cannot stick out. And it's a lattice line because the boundary is a lattice line. And what we get is that it's an exponential interaction. So such a hole will be exponentially strongly attracted to this boundary, and it will be exponentially strongly repelled by the other boundary, by the top boundary. That's the interaction you get. So I don't know if it's surprising or not, but this is what one gets. So the question is, how about other boundaries? Well, one thing about this boundary, yes?
This is a reflection of the fact that in the Kinyon-Okumuko picture, you know that the parameter of slope is varying along. So it's like a defect sees a background. So
yes.
Sees a free energy which is varying.
Yes, yes, exactly. Yes.
For this reason, there is the exponential.
Yes, yes. But also, specifically, what happens, I mean, if you think about how do the triangles that touch the boundary on the other side, how do they look? They all look alike. They all point downward. So, they point downward, the hole points upward. So it's like this cumulative effect of, overwhelming attraction, right? At the other end of the spectrum, you could have a zigzag boundary, where on the other side of the boundary you have up pointing, down pointing, up pointing, down pointing. So it's like a neutral boundary. And it's an interesting question. How will holes interact with such a boundary, right? So this case I can also do. And what do the colors mean? Well, the colors mean the following. So this is the interaction of a boundary with a slight defect. The boundary itself has a slight defect because these two zigzags do not line up completely. And the blue ellipses, what they mean is that those lozenge positions are weighted by 1/2. Okay? So you see, I mean, you take a lozenge tiling of the complement of the holes. Sometimes lozenges occupy blue ellipses, then they acquire a weight of 1/2. And the weight of the entire tiling is the product of all these 1/2s. Right? And then you sum over all these weighted tilings, right? So, of course, I can get the interaction also with, I can send this monomer to infinity, this boundary, this defect in the boundary to infinity, and then you get just the interaction with a boundary purely of this kind, of a boundary purely of that kind. So this generalizes the zigzag boundary, but I put it in because, we can do it. And what turns out, so the question is, how will this interact with it? Is it exponential? Is it polynomial? And if it's polynomial, what is it? It turns out that, And this is just how to define the correlation. The correlation near the boundary can be defined as follows. You look at the number of tilings of the region with the holes here. And again, divide that by the number of tilings of the region with the holes in the reference position, right? But now you keep these holes as they are, and only this part of the boundary goes to infinity. So the holes fill the boundary, right? The holes fill the boundary. So that's why I call this omega B, or omega C. Sorry, it's constrained boundary. Okay. So what interaction do we get? Well, it turns out that what governs this situation is the method of images. It's the method of images from electrostatics. So you just reflect the picture. So notice in the middle you get a monomer because of the defect. So this is quite interesting. So that defect in the boundary gives rise to such a monomer. And the monomer is half black and half green because I denoted by green the images. So this is a combined effect of the original and the image. And it turns out that if you take this symmetrically, this picture completed by symmetry, the boundary, the correlation near the constrained boundary of a family Q of holes is simply a constant times the square root. You need to take the square root of the correlation in the bulk of the collection of holes together with its reflection, which also notice gives rise to this monomer. Okay, so this I can prove, and this is another electrostatic analog. So this seems to be like a conductor or something, right? And the exact formula is kind of long, but it's very explicit. So this is what I mean by a multisum of round things. So this is the exact expression for this B should be C. Sometimes B is boundary, sometimes C is constrained boundary. But anyway, all these parameters, R1, V1, Rm, Vm, and so forth, they specify the locations of these holes. That's all they do. And then notice this is not the asymptotics. It's at finite distance, right? It's the exact form. The exact form of the correlation is a multiple sum of round terms. Round terms, just ratios of products of factorials. And you can do what you want with this because it's exact. I mean, of course, the asymptotics may be hard, but in principle, you can. Anyway, on the half hexagon. That's right. Yes. The V's are so R's and V's are the coordinates of the holes. So R is the distance, the horizontal distance from the boundary, and V is the vertical distance from the defect on the boundary. Yes. So yeah, that's a good point because from this formula you can basically almost see how the Coulomb interaction will kick in because you have all these differences and anyway, and it's interesting that the effect of the monomer will come from all these factorials. It's a bit non-trivial. You just have to work out the asymptotics, and that's the effect of the monomer. Is the effect of a monomer at the middle. Okay. So, for instance, if you have just one hole, so you have this boundary. And you have just one hole, at distance r, you get it as a sum of r squared round terms. So it's not too bad at all, and you can determine many of its properties. Okay, so I think this is what Andrea was saying in a talk. So in a previous talk. So you said that on the boundary you can have monomers and you don't care what they do. So this is equivalent to the following picture. I call this a free boundary. So you have a hole, let's say, of size 2, and we're interested what will be the interaction with a lattice line boundary which is free. Because if it's not free, if it's constrained, we saw it's exponential, right? But what is the effect if the lattice line boundary is free? So by free, I mean that lozenges can stick out, which is equivalent to saying that you can allow monomers on the boundary anywhere, right? So this is a problem that we looked at recently with Christian Kratenthaler, and we figured out how to do it. But in general, when you just look at this problem, the question is, how do you do it? I mean, there seem to be no methods in the literature. There's no there's no coupling function near a free boundary, or it's asymptotic. At least I don't know how to do it that way. So, fortunately, we have this quote by Arnold, who said that mathematics is a part of physics where experiments are cheap. So you can just design an experiment to get the answer to your question. So what is the experiment? So remember, we're free. We have all this freedom of how we define the correlation, right? So we can, for instance, include this hole in half hexagons, in large half hexagons, halves of regular hexagons, let's say, which are free on this side, right? And then we look at the number of Lozenge tilings of the thing with the hole, and we divide it by the number of Lozenge tilings of the thing without the hole. And then we just repeat the previous steps. You take the boundary to infinity, that will give you a correlation. And if you're lucky and you can get your hands on this number, then you're in business. You can just do the asymptotics, right?
May I ask
Yes?
why the mirror method was not working
Here? In this case?
in the free boundary?
Yeah, okay, that's a very good question. So actually, right, so I said all this. So the mirror method, it's a very good observation. The number of Lozenge tilings in the previous slide, so the number of Lozenge tilings of the half hexagon with free boundary here, obviously by mirror symmetry, is equal to the number of Lozenge tilings of the hexagon with two symmetrical holes, Lozenge tilings which are themselves symmetric, because you just reflect, right? So this is indeed a very valid point, but it seems to be hard to compute this number. So if you have no holes, and you just take a complete hexagon, and you want the number of Lozenge tilings which are vertically symmetric, this was a non-trivial problem. McMahon thought a lot about this, and he conjectured the result. He couldn't prove it, and then we have 4 different proofs available now. So Andrews, McDonald, Proctor, and Christian Kratenthaler, they all have different proofs for this. In the case with no holes, so this is highly non-trivial work, right? So it's very hard to find this number. And actually, I was interested in this number, and I found a conjecture which I guess physicists may be interested in. So I conjecture that the number of Lozenge tilings of this, with no symmetry requirement, just the total number of Lozenge tilings of the hexagon with 2 symmetric holes, is equal to the product of 2 numbers. One of the numbers is this number, the number of symmetrical Lozenge tilings. And the other is the number of symmetrical Lozenge tilings, but with respect to the horizontal symmetry axis. Right? So it's a conjecture. And we're working on it with Christian. We hope to have it, and generalize it. But anyway, so again, the fact is that the total number of Lozenge tilings is equal to a product of 2 symmetrical Lozenge tilings. Symmetrical like this, and symmetrical like this, with respect to the horizontal symmetry axis. Anyway, that was just a curiosity. But okay, but actually, that's how I conjectured the exact formula. Because if you have that, anyway, it's helpful. It's helpful in conjecturing the formula. And the formula we proved with Christian is the following. So f and x is just this guy with length 2n here and 2x here. So n and x just gives the sides. And k is equal to 2 in this case. So k is equal to the number of long diagonals of lozenges that separate you from the midpoint here to the vertical axis. Okay, so triangle left sub 2 is the triangle that you remove. Okay, so this is the formula we managed to prove with Christian. The number of free Lozenge tilings with this hole is equal to this expression, which, as you notice, it's pretty nice. I mean, all the factors are round, and you have a single sum. So, it's helpful, right? And this was a lot of work to prove this formula. But once you have it, then you can do the asymptotics, and here's what you get. First, you can define the correlation near the free boundary. F stays for free boundary. K is the distance of the hole from the free boundary, and R is the ratio of the 2 sides of the hexagon, right? So. This is free. this is 2n, this is 2x, and x over n go to infinity so that the ratio approaches r, right? So r should be 1 for us, but it's still interesting to do it in general for r. And if you do this, yeah, this should be r here, because r is here, right? So you get that the asymptotics is this. So it's in terms of these Laplace integrals. So again, it's not the asymptotics. It's the precise correlation at finite distance, right? So it's the correlation near the correlation function near the free boundary at finite distance k. So it's exactly this Laplace integrals. And then you can do the asymptotics as k goes to infinity, because you just these are Laplace type integrals. So you apply Laplace's method, right? And it's interesting that you get this exponential interaction unless r is equal to 1. So I want to emphasize this. It's a bit surprising, perhaps, first. By the way, the same happens without the boundary in the bulk, if you go back to the previous pictures. But this is just an illustration of the fact that the interaction with the boundary is so strongly exponential, so overpowering, that it somehow reaches all the way into the middle. And unless these miraculously cancel out and you get polynomial interaction, you get this exponential interaction. So anyway, but if you do it correctly and you take the half of a regular hexagon, which is the way this thing should be done, then you get this polynomial interaction. It's like 1 over 4 pi times 1 over the distance to the free boundary. And this is again, it's again like the method of images, right? Because you know, this is the whole, this is omega f, and if you take the image, you get the correlation in the bulk. So it's again a constant times the square root. Okay, so you can take this one step further as follows. Suppose you put here a blocker or something. So at this particular place, the lozenge cannot stick out, cannot protrude out. Okay, so what does that mean? I mean, remember, that means that on the other side you would have this unit triangle, which has the opposite orientation, right? So something happens there. Okay, so let me call this charge density. So the charge density is the scaling limit that this happens, that there's no lozenge that sticks out there, right? And there's strong evidence that the charge density is this, which you know, it's exactly what you have in physics. So in physics, you have a charge near a conductor. It attracts all the free electrons, and it produces this charge density, and it has exactly the same formula as before. So somehow, you know, these free electrons, you know, around, you know, on the other side are attracted, and you know, this effect is produced. So it's yet another parallel to the electrostatic phenomenon. So it's at a more subtle level. Okay. Right. So we can also talk about corner effects, right? So what interaction does this lead to, right? So we need to define it. So what I do is it's a 60-degree wedge with zigzag boundary. We agreed that zigzag boundaries are nicer because the straight line boundaries give rise to this exponential interaction. And let me do constraint. Somehow free seems to be harder. So let me do just constraint. Well, we expect the method of images to work, right? But now you get all these 5 images because you get images of images and so forth. And okay, so can you do it? You can do it. Okay, so this is work in progress. But you know, it's clear that it can be done. I just haven't done the calculation yet. And how can you do it? Well,
is this without 1/2 on the boundary?
Pardon me?
You have a 1/2 if an edge is...
No, there's no 1/2. There's no 1/2. As it turns out, the 1/2s don't matter so much, actually. But and I'm pretty sure you could have them if you wanted here. But as it is, they aren't there.
Because without the 1/2, it's not that 6 copies of these really tessellate.
Well, I mean, you know, you have to worry about everything which doesn't seamlessly match is put into the multiplicative constant in front. So, yeah. Okay, so approach for proving this is to, yeah, I'm really frustrated with this. I mean, it looks a lot better in high resolution, but I think you can still understand what's going on. So I chose a specific region on the triangular lattice, which has zigzag boundary here, straight line boundary here, that's zigzag boundary, and straight and straight. And it turns out that, and it has this hole. And notice that if this side is equal to 0, you get back the wedge, and then you just have these two additional things. But in combinatorics, any extra parameter is to be treasured because it gives you ways to compute things and prove things. So I keep it here. And anyway, so there's this hole of side 2, and I claim that the number of lozenge tilings, the exact number of lozenge tilings of this, is quite manageable. What do I mean by quite manageable? It will be a double sum of round things. Okay, how come? Well, in all this business, by the way, in my approach number 2, which I said it's non-Pfaffian, I don't use Pfaffians, I use encoding by lattice pads.
That's not true. Those Pfaffians appear.
They appear with a free boundary, but they don't appear here, actually. It's just determinant. But anyway, they appear in a different way, not in the Pfaffian method way. But, right, so here you see a tiling, at least I hope you can see it. So, these edges are not so clear, but we have, here, for instance, we have 2 lozenges, and then I just followed lozenges around. So I think of these as starting points, including these, and these are ending points. And then I just follow lozenges in my tiling. And then I get these non-intersecting paths of rhombi. So it's a bijection. So tilings are in bijection with these families of non-intersecting paths. And more to the point, the crucial thing is that families of non-intersecting paths are determinants, Gestel-Vino determinants. Right. So what you can do is you can, in this determinant, rows are indexed by the starting points, this, dot, and this, and this. These are all starting points. And columns are indexed by ending points. And it's a determinant, so you can apply Laplace expansion along the red rows. So this is just a generalization of expanding a determinant along a row. You expand along 2 rows, and you get a double sum. The factors are nice, are just 2 by 2 determinants of binomial coefficients. But it turns out that the cofactors are also nice. Because the result for the cofactors can be interpreted using backward Gestel-Vino as, again, being tiling numbers, numbers of tilings of dented regions. And the dented regions are these. So you just, strike out the ending segments. And then the whole is no more because you did Laplace expansion. So the crucial fact is that these regions, the number of tiling is almost round. What does almost round mean? So it's a product. There's no sum involved. It's a product, and all the factors are linear except for a single one, which is quadratic. And you can work with that, right? So using that, you can do the calculation, and I haven't finished it yet, but I'm quite confident that it will verify the predicted corner interaction with many images. Okay, so now another thing you could look at, I start on the first slide we had the dimer problem. That's the number of domino tilings of 2n by 2n square, and that's nice. So we know about even squares, but how about the odd ones? What can you say about the odd ones? Well, if you have an odd square, and you want to cover it by dominoes, always the monomer will be left, right? But there's nothing wrong with that. You could still look at those numbers. And for instance, a natural thing to do would be to place the monomer here, see how many tilings you get, and plot that number above it, right? Place the monomer here, plot them, and you get this plot, right? This discrete plot. And this determines probability. This defines the probability distribution. So it's kind of an interesting question. What will be in the scaling limit the density of this probability distribution? So will you have more tilings in the middle or not? And We are on fairly familiar territory if you think about it, because we talked about the interaction with the constraint boundary. Now, if you go on the other side, you have black, white, black, white, black, white. So it's like it's the method of images when the image has the same sign. We saw corner effects, images. So you should do images everywhere, and then you get this, periodic picture. And doing some. This is joint work with David Wilson, and doing. Using some assumption of conformal invariance, we were able to conjecture this explicit density function as being the answer to the problem I just talked about. So, we sent the lattice spacing to 0, but we rescaled a square so that it's the unit square, right? And f is the density function, and z0 is the position of the monomer.
What is the difference between z and z0 now?
No, it should be z0. Yeah, right. So z0 is the location of the monomer, and script p is the Weierstrass p function, and k is the complete elliptic integral of the first kind, and then you have the answer in terms of the Weierstrass p function and this derivative in this way. You can do this in Mathematica, and David did it, and you get this nice birthday cake, which is appropriate because today is the birthday of my son. He's one like one monomer. So, yeah. Okay. Thank you very much. Yes.
Could you imagine an analog of the screening effect in electrostatics if you consider the gas of defects? Do you think you would have a kind of screening? Would it attract other charges that will replace the potential by an exponentially decaying potential?
Is this related to the intrinsic strengthening of the field at very small distances because of this cloud of...
Exactly.
Yeah, that's a very good question, yes. I think so, yes. So remember, I have the exact formula, after all, for... I have the exact formula for the holes when suppose they're just two holes, right? And at finite distance. I have an exact formula for that, right? And the Coulomb picture takes over in the asymptotic limit. So it makes a lot of sense to ask how exactly do we reach this limiting behavior? And whatever happens before would correspond to screening. So I expect some. In fact, in some cases, I did some calculations, and it does look that you do get intrinsic strengthening. But to give you a meaningful answer to that, I will need to define the field. And actually, the field, I did. It just takes a minute. I do have the field. Okay, so there's interesting things to be said about what happens on non-bipartite lattices, but I guess I don't have time for that. But for a field, you could take, you have your holes and look at the left-pointing unit triangle outside the holes, right? Then this will be covered by one of three lozenges. It's either this one pointing to the right, or to the northwest, or to the southwest, right? And you could take the average orientation. You could take the average orientation of this hole, and this defines a discrete field. And if you have two holes, you get this field, this discrete field, which looks a lot like the Coulomb field. And I guess what you're asking is how exactly the picture from here approaches in the limit this picture. And at a small distance, you have some effects which would correspond to this. So this would be the analog.
But it's more at long distance, actually.
Well, so is it? But is it a correction to the? It is
something completely essential for the thermodynamic limit to exist for long gas.
Well, yeah, I don't know. Maybe I didn't understand your question perfectly. So we can talk about it later. Yeah. Yes.
Question you. In some cases, Coulomb gas gives you long range interactions like logarithmic potential.
Yes.
And in some cases, you seem to have screening, right, with exponentially strong interaction.
Yes.
Which is screening.
I see.
So it was not clear to me, how you have this kind of screening effect sometimes, and usually logarithmic potential. Like
Yes.
Coulomb gas.
Yes. Well, I mean, so in the cases I mentioned, they were due to the boundary. And when you have this constrained boundary on the triangular lattice, all the unit triangles on the other side of the boundary have the same color. Somehow it's this extremely strong cumulative effect. I mean, I don't know how to explain it more than that, but I mean, it seems to reach all the way into the middle, right? As I said here, if you scale so that the ratio does not go to 1, you have exponential interaction even in the middle. So this is an artifact from of the region, and remember, we're free what regions we're free to choose whatever regions we want for defining the correlation. So these regions were chosen so that we can have some results and compute the correlations. But so another possible answer to your question is that you do get exponential interaction in the dimer model if you have holes, if you're non-critical. If you're in a non-critical situation. So yes, and actually this matches with the Kenyon-Okunkov and Sheffield classification of the dimer model. They have these 3 phases, and if you get this exponential interaction if you're non-critical, and that is reflected also in they don't have holes, right? They look at the fluctuations of the height difference, right? But if you take holes and look at the questions I have been looking at, the asymptotics of the correlation function, you again get exponential interaction if you're in the non-liquid phase. So that's also a possible source of, I don't know if you would call that screening, but it's exponential.
But in your case, it do coexist. These two kinds of behavior.
Yes.
Do coexist.
Yeah, that's a good question. So for the examples with the boundary I presented, all the weights were equal to 1, except possible for some 1/2. And that would be in the liquid phase. It would be in what they call the liquid phase, Kenyon, Okunkov, and Sheffield. And in that, I mean, for the liquid phase, they get just polynomial interaction. So I don't know if I would, yeah, I mean, but it's an interesting question if they could coexist, I mean, for certain choices of weights. Yeah. And probably they do, actually. Yeah. Yes?
Another question about screening. I mean, the screening you discussed here is like short distance screening only.
I think so, yes. What I tried to explain, yes.
It's opposite to what Bertrand discussed, namely the screening that makes the interaction exponential at long distances.
I see, but those two do not coexist. That's right. So what I explained was for the long-range Coulomb interaction. So at short range, I don't know if it's exponential, but there's a correction because there's a correction, right?
Exponential doesn't mean very much in that.
Yes, exactly. So, yes?
But then, are you able to consider the situation that there is a gas of these defects?
Yes.
And then how that affects the interaction between two defects that are fixed.
So the gas of defects would be a gas of monomers or of triangles of site 2, for instance. And then on top of this, you have two fixed defects of site 2, for instance.
Perhaps bigger or...
I see. And when you say a gas, their number has to be infinite, right? I mean, you have to have positive density. Yeah.
So you want to do screening.
Yeah.
And then you would have real screening that
I see.
that could possibly depend on the size of the charges. I mean, I'm sure I can give you a conjecture whether single triangles would suffice.
Yes.
Wait a second. I would imagine that single triangles would turn the Coulomb interaction into exponential.
Yes.
While double triangles, size 2, would not.
I see. Yes. So,
Please prove that.
so is there a simple reason for that? And already the change would happen already at going from size 1 to size 2?
I'm just guessing, but I can calculate that. With, well, the reason is that smaller charges are more relevant in the renormalization group sense
Yes.
than larger charges, because larger charges cost more energy just to be there.
Yes.
For the electric field that they generate. And so they are less dangerous because they cost so much energy that they will not do very much.
I see. Yeah, well, that also agrees with the fact that in the dimer picture, if you have a larger hole, it will dislocate a lot of things and it will be compatible with a lot fewer configurations.
Yeah.
Yes.
Yes.
Yes. The other interesting thing that this reminded is that in this picture we don't have energy. I mean, all the energies are the same, so it's a purely entropic effect, because my configurations are tilings and they all have it's a uniform measure. So it's an interesting difference between this and other Coulomb gas models I know of. I mean, perhaps there are some others that are purely entropic, but I think the ones for instance, one is in the literature that I know of seem to be mostly defined in terms of Hamiltonian. So you have these energies, and so anyway, it's
No, not all, but what is also particular in this case that you have pure Coulomb interaction, just only a product of binary interactions.
Yes. Yes. That's right. It's just a product over. So it's the superposition principle works basically. So it's equivalent. Yeah.
So there's no background charge.
Yes. Yes.
One more. We're good.
You showed us how these holes were actually electric defects, right?
Yes.
Electric charges. Is there a way of also enforcing vortices or magnetic?
Yeah, that's a very good question. Yeah. Yeah. So it's if you have the Fisher-Stephenson correlation is mediated by dimers. It's monomers in a sea of dimers, right? I mean, when you have a boundary, you may say that you're close to the shore, maybe, and there's a free boundary, or close to a wall, and it's constrained boundary. But in this case, you're in a sea of dimers, and that's how you define it. A sea of dimers is just one factor, right? Perfect matching. So there's nothing wrong with two factors. You could look at two factors. You could mediate your interaction by two factors. Right? And then it's a simple bijection. You just take complements of edges. And if you look at all the edges which are not included, then you get dimers. But the holes become, these triangles of side 2. Because, here, there's no edge. So if you take the complement, all three edges have to be there. So 4 edges are there. It's kind of interesting because the even case pops up naturally. And I can do the even case. So in this case, I can prove the monomer-monomer correlation. More than just, much more. Any distribution of monomers, corresponds to a bunch of triangles of size 2 in a sea of dimers, which I can handle. That's a curiosity, but it just leads to the question you asked. So if you assume universality of this closely packed loop model and you pass to the square lattice, then you get monomer defects in closely packed loops. And if you these are equivalent to these ice configurations. And then you get sources and sinks. So it's the source-sink correlation in an ice state. And if you just rotate by 90 degrees, you get vortices. So this is a conjecture, but it solves conjecturally. Modulo the assumption of universality, you get this interaction. I think it's called stiffness. You get it explicitly. And as I said, if you rotate, you get vortices. So I don't know if that answers your question, but yeah.